Okay, today we are going to talk about the quantum theory and the beginnings of the quantum theory, which is basically the modern theory of where electrons are located, unlike Bohr's model, where Bohr's model had the electrons on a specified orbit and it's two-dimensional and they don't move from that. Well, they can't be in between the orbits. We're going to look at the modern theory, the quantum theory. And so we're going to go through Heisenberg uncertainty principle, Schrödinger, and into quantum numbers. So if you think about your address, you don't have to write it down, but think if you go from the most general, where you live, it would be like the U.S., and then you can get it narrowed down to the state, and then you can narrow it down to the county, town. Same thing that goes with the quantum numbers. We're going to be describing where the electrons are located, and we can go from more general, like which energy level they are. We can go to sublevels, we can go to orbitals, and then specifically what spin state they have inside an orbital. So how many students would have the same zip code in here? Well, there'd be Hastings or Juniata probably would be your... No? What? It was... Yeah? What? No, Juniata is different than Hastings. No? They have a different post office. But you would have many of you would have the same zip code. What about the same street? Maybe a few, not as many. What about the house number? You each have a different combination of those three, right? That's going to in the same way that no two houses have the same address, no two electrons in an atom have the same address or the same set of 4 quantum numbers. So you're going to each electron has to have it can have the same energy level, same sublevel, same orbital, but they'd have to have different spin state. Or maybe they have the same spin state, but they're in the different orbital. So somehow those 4 quantum numbers, at least one of them have to be different between 2 different electrons. And so we'll learn what those quantum numbers are. Tomorrow we will learn, it's called the electron configuration. It's how we specify what their address is or where they are in the atom. So we're going to look at de Broglie's involvement in the developing of the quantum number or quantum model, compare the 2 models, and look at the Heisenberg uncertainty principle and Schrödinger's wave equations. And then we're going to look at finish up with quantum numbers. So de Broglie was studying the electron, and he proposed that electrons have wave-like properties, just like light, and it followed that electron waves can only exist at specific frequencies. Just like light had to have a specific frequency in order to have a certain amount of energy for that. Remember the photoelectric effect? It had to have a certain frequency, had a certain amount of energy to give the electron enough energy to bounce it off. That he proposed that electrons also had those same properties. And what he studied, what he specifically looked at, which proved that they do have wave-like properties, is diffraction and interference. So he saw that electrons, like light waves, can be bent or diffracted. And so passing light through a prism is a way to diffract light, or it bends light and makes it so you can see the different colors. So electrons are able to be diffracted as well. And they can also interfere with each other. And interference is when waves overlap. And how you can think of when waves overlapping, if you drop 2 stones into a pond and you see their waves ripple out, eventually they're going to overlap each other, right? And so you can see where sometimes the wave would be a little higher, a little bigger, because the 2 peaks interfere with each other. Or maybe the wave would be a little smaller or no wave at all if their trough and peak overlapped each other at the same time. So there's different ways that you can interfere, but electron beams can interfere with each other just like light waves or any other waves. Okay, Heisenberg. How many of you guys watch Breaking Bad?
Yes.
He calls himself
Heisenberg. What? Yes.
this guy. Yep.
So, does that mean all chemistry teachers know how to cook crystal meth?
No. Heisenberg has nothing to do with cooking.
Yeah, but I'm talking about he's a chemistry teacher.
I know.
And he can cook pure crystal meth.
No, I don't know how.
Okay. If you did, you wouldn't be here anymore. You'd be way rich.
Right. So Heisenberg proposed that if you tried to measure the velocity of an electron, you couldn't measure the position at the same time, or vice versa. If you're trying to measure the position of an electron, you would knock it off of its course, and you can't get the velocity at the same time. So the Heisenberg uncertainty principle states that it's impossible to determine simultaneously both the position and velocity of the electron or any other particle. So if you tried to, it's kind of like an airplane propeller. So an airplane propeller, if it's spinning so fast, are you able to see a propeller, one blade? No. Could you measure the velocity of that propeller? Yes. If I wanted to measure or find where the position of that blade is, I'd have to slow it down and stop it and find the position, but that now changes the velocity. So when you try to measure one, you can't measure the other. So that's what Heisenberg uncertainty principle is stating. Okay, Schrödinger was an Austrian physicist, and he developed these equations that describe the wave properties that electrons have. And together with the Heisenberg uncertainty principle, that was the foundation for the modern quantum theory. How many of you guys have ever, what kind of graph would have a wave, would look like a wave? What kind of graph looks like this? You seen that kind of graph before? No? Have any of you guys ever graph sine or cosine? No, I don't know which math class you do that in. Okay, so this is a sine or cosine wave, a graph, and so his equations included sine and cosine because it obviously already graphed itself as a wave. We aren't going to look at the exact equations, just that they are wave equations. So what these equations did is that said that electrons don't travel around the nucleus in neat orbitals as Bohr postulated. So as Bohr's model had them going in this certain specific path around the nucleus, instead they exist in a certain region called orbitals. So an orbit is a two-dimensional path that the electrons have to stay on. An orbital is a three-dimensional region that it indicates the probable location of an electron. Because you can't specifically find the position of an electron, it's all based on probabilities where the highest probability of finding an electron would be. Okay, let's, it wasn't the greatest video, but we'll watch it here.
It is very difficult to predict the position of any given electron at any given time. There are, however, regions inside the atom where electrons are likely to be, and other regions where electrons are unlikely to be.
Okay, so they're just regions of space where they're likely to have an electron. So we use quantum numbers to describe where electrons are located. And these quantum numbers specify properties of atomic orbitals and the properties of the electrons in the orbital. So we have four quantum numbers. The first quantum number is the principal quantum number, and these 4 are all going to describe something different about these orbitals. The principal quantum number is symbolized by the letter n, so you can have n equals 1, n equals 2, n equals 3, and it indicates the main energy level. And so when we say n equals 1, we're saying it's in the first energy level, versus n equals 2 would be the second energy level, and the higher the energy level, the farther away from the nucleus you're getting. So this would be like an n equals 1 sublevel. This is an n equals 2. So you can see the difference, that the larger the n value, the larger the electron or the orbital, because the electrons could be farther away from the nucleus in this orbital. If we look at the periodic table, we'll use this more tomorrow, but when we go down on the periods, 1, 2, 3, 4, 5, 6, 7, these are going to be our energy levels. So this would be the first energy level, second, third, fourth energy level, and so forth. The angular momentum quantum number is symbolized by the letter L, and it's just telling us what shape the orbital has. So orbitals are not just spheres. They have different shapes. We have, here, let's write something up here also. So an L value is always from 0, L will equal 0 to n minus 1. So let's say if n equals 1, what would L equal? Starts at 0, so we'd always have 0. And then what would n equals n minus 1 be if n equals 1? 0. So is there any other possibilities for L? No. But let's say n equals 3. Then what L values would we have possible? 0, 1, and 2. Because these are the integers from 0 to n minus 1. Okay, so we have 3 possibilities. Now, instead of using numbers all the time for L, because that kind of gets confusing with the n numbers, we use letters. So if L equals, for an L value of 0, that means the shape, we call that an s orbital. An s orbital is a sphere. This would be an s orbital. If L equals 1, we call that a p orbital. A p orbital has 2 lobes. It looks like this. It has 2 lobes on it. Kind of like they sometimes call that a dumbbell shape. If L equals 2, that is a d sublevel. And a d sublevel has 4 lobes. 4 lobes on it. And then also we'll see later there's a couple different orientations of it, and one of these orbitals look like this. This is also a d sublevel. And n equals 3 is called an f sublevel. And I don't have a model of that, but it basically would look like this, I guess. Let's.
So the highest n can reach is 3?
No, we will go up to n equals 7.
Okay. For right now, just 3 now? Or is it?
No, for L value, for shapes, we'll only have S, P, D, and F. But our n values could go larger. So you always have more possibilities. It doesn't mean there's an electron in those. So even though if n equals 4, that's where we're going to have 0, 1, 2, and 3. So S, P, D, and F. That doesn't mean all of these sublevels have an electron in them. Maybe you only have electrons in the S sublevel there, but there's always more possibilities. So same with like when we get up to n equals 5, you'd have 0, 1, 2, 3, 4. So you'd have 5. You'd be S, P, D, F, and there's a G sublevel. But G sublevel is only used if they're in an excited state. So there's a possibility of a G sublevel. There's normally no, in the ground state, there's no electrons in the G sublevel. But it's still a possibility. Does that make sense? Kind of. An F sublevel looks kind of like this. They're kind of angled out a little more, but it's basically two of these on top of each other. So. Is there anything else I should talk about there? Okay, we'll go on. And then the last two is the magnetic quantum number, which they represent with the letter M. And it's going to indicate the orientation of an orbital around the nucleus. So let's look at our S orbital, our sphere. Is there any way I can orient this around, the nucleus is right in the middle. Is there any way I can orient that to get it a different shape or different orientation? No. So there's only one orientation. So the S is called the sublevel, but there's only one orbital in the S sublevel.
So then n will equal 1?
N equals 1. You can have an N equals 1. You can have an N equals 2.
But what about
M would be 1. Yes. We don't really assign them. It would have a value of 0, but there's only one M value. We don't really assign the numbers in this right now, in this class. But if you have an N equals, you can have N equals 1 and an N equals 2. They're both S sublevels because, remember, let's write this down here. Let's say if N equals 1, L would be equal 0. If N equals 2, you'd have a possibility of a 0 and 1. So this would be S, and this is S or P. So we have a 1S, and we can have a 2S. And what did the N values describe? The energy level. Yep, principal quantum numbers, and it's the energy level. So the farther away than from the nucleus. So this could be a 1S versus a 2S. So electrons can be farther away in this this orbital. So you can have a 1S, 2S, 3S, 4S, 5S. Those are all S sublevels. They're just going to be in different energy levels. Okay, what about P? So let's see. Let's say S has one orbital. What about P? The P sublevel. Now I could take this and orient it on the x-axis. Could also orient it on the y-axis, or I could orient this on the z-axis. So you have 3 different orbitals in this sublevel. Okay. So for the P sublevel, there are 3 orbitals, 3 orientations. Now in the atom, you don't have like this orbital over here, this orbital over here, and this one over here. They're all overlapping. So they're all, it's hard to do with this, let's do it this way. The nucleus would be kind of where that white part is, but they'd all be overlapping like this. If you ever are back by that poster over there, you'll see in the right, bottom right side, there's the red sphere, that's an s orbital. The green blob thing is the p sublevel, and it has all 3 orbitals overlapping and over each other. Then the blue one is the d sublevel, and the f is and the orange is the f sublevel. So it shows how they overlap each other. But this is just, so that has all 3 orbitals. The green has all 3 p orbitals just overlapping on each other. Okay. Also, we have s sublevels. Before we have p sublevels, we have the s sublevel. So this would be, so let's see, we have all the p sublevels overlapping each other, and then we'd have like this, but then we'd have this s sublevel in there too, and they're all just building on each other and getting to be this big blob. Okay. And these are what you call the electron clouds. So electron clouds aren't just spherical. They have different shapes. Okay, the d sublevel. How many orbitals do you think it would be? Look at our pattern.
6.
5. We are going up by 2s, an odd number. I'm not going to build them all. But you have a d sublevel like this, and then like this. You have one like this, and then you have this 5th one. Okay, so there's 5 orbitals within this sublevel. And then what about f? What do you think? Right. And I don't have the model kit to build an F sublevel. Okay. Then the last quantum number is the spin quantum number. And it is showing whether the electron, because the electron is spinning on its axis just like the Earth spins on its axis. And it can spin clockwise or counterclockwise. And so the spin quantum number is telling you which direction the spin is. The spin state is either +1/2 or -1/2. +1/2, it doesn't matter if +1/2 means clockwise or counterclockwise, but they just have to be their opposite. And in an orbital, so in one orbital, in this one orbital, you cannot have 2 electrons with the same spin state. So you have to have a clockwise and a counterclockwise. But you can have 2 electrons in this orbital. You can have 2 electrons in this orbital. You can have 2 electrons in this one, and this one. So we have 3 orbitals within the p sublevel. And the p sublevel, how many total electrons are possible? 2 here, 2 here, 2 here. So it's a total of 6. Right. Total of 6. How about in the d sublevel? How many electrons would be possible? 10, because we have 5 orbitals. Each orbital holds 2 electrons, maximum. Now, it might not be filled. It depends on what element you're looking at. But you have a maximum of 5 orbitals and 10 electrons. This clear as mud so far? Okay, this is one part that you're really going to have to picture in your mind, and you got to think these atoms are so tiny, and yet this is all going on in it. Okay. Let's look at, this just talks about energy levels.
The principal quantum number n is a positive integer describing the energy level of the electron. For example, an electron for which n equals 1 occupies the first or lowest main energy level and is located closest to the nucleus. The angular momentum quantum number L can be any integer from 0 to n minus 1 and describes the shape of the orbital. The s orbital can be represented by a sphere. The p orbital can be represented by a dumbbell shape. The d orbital is primarily shaped like cross dumbbells, but can also have a 5th dumbbell ring shape. The magnetic quantum number m can be any integer from -1 to +1 and describes the orientation of the orbital. Orbitals run along the x-axis, the y-axis, and the z-axis, as shown in this p orbital. The spin quantum number has only 2 possible values, positive 1/2 and negative 1/2, which indicate the two fundamental spin states of an electron in an orbital. A single orbital can hold a maximum of 2 electrons, which must have opposite spins.
Why do you think they use an up and a down arrow there when we're talking about the spin quantum number? Why would there be an up and then a down? They're spinning opposite directions. So tomorrow we're going to look at electron configurations and orbital notations. And so we're going to show exactly in an element where each of those electrons are located. And we'll use some arrows like this to show their spin state. Here's just a picture, S orbital, P, and then these 5 are the D sublevel. Okay, and then they have some equations that you can use to determine how many orbitals, how many electrons. We're going to go through and I'll show you how to do that based on just counting orbitals and stuff. Now here's where you can see, okay, if L equals 0, which shape are we talking about? S. So this is S. What about when L equals 1? P. 0 is S, 1 is P. What about 2? D. This is S, this is P. This is D, and N equals 3, or L equals 3 is an F. This is where it shows the actual M values. So M can be from negative L to positive L, and you guys don't need to know the actual values. Or S, negative L and positive L still just stays 0, so that's why we only have one orientation, one orbital. Whereas when P is negative 1, we can go negative 1, 0, 1, so there's 3 orbitals, which we already talked about. Be these 3 right here. These 3 orbitals, this is showing how many. When you have D is 2, you go from negative 2 to positive 2, so there's 5 orbitals. And then for F, we go from negative 3 to positive 3, which is why there's 7. Okay, so that's basically just showing you the numbers behind the M values. Okay. And that's it. So we're going to try, what color of ink should I use? I don't know if yellow is going to show up here. We'll go green because I think Kylie said green. Yellow, I really don't think yellow will, if I use this yellow. So let's say N equals 3. Let's answer some questions about this. How many sublevels are there? There's 3 sublevels. What are they? 0, 1, and 2, or S, P, and D. Yep. Good. How many orbitals are there? No. Total. So S has how many orbitals? P has 3 and D has 5. So how many total? 9. So there'd be 9 total orbitals possible. So then how many electrons? Right. 18 electrons. Because we have 2 electrons in each of these orbitals. Now, it might not, on the worksheet here, you will have questions that you'll have to answer this kind of thing, but maybe it'll skip right to how many orbitals, or maybe it'll skip right to how many electrons. So you'll just go through that same process to answer those.